Hello. Many interesting mathematical objects are vector spaces. Yep. Okay, so such that x is larger than 0, which means it's on the right hand side of the xy plane. Our goal side, which of the following properties of a vector are satisfied. Let's consider for this question the closed under addition question. If u and v are elements of T, then we have u u1 and v1 are both larger than 0. Since this implies that that's larger than 0, we can conclude that u plus v in this case would always satisfy that our x value is going to be positive. Must have an element of T. This works for two vectors in T, so this is a formal proof that T satisfies the property of closure under addition. Property 6, closure under multiplication. At first glance, this might seem to hold as well. However, we can guarantee that something, it's always larger. Yeah, so it seems like scaling might be a but. Keeping the first component of your non-negative is what keeps them in T, so it might come as no surprise that the reason this probably doesn't hold is because we have a scalar in the real numbers. We only need to determine a single failure, so let's choose a concrete counterexample. If we choose this as 1 and choose scalars minus 5, then the scalar is like that because the scalar of v1, so this is the specific value, not the specific v. Yeah, because v1 is actually minus 5 and it's less than 0. Since we only need one counterexample, it shows that it doesn't satisfy, so it's pretty easy. Okay. Suppose that this is the set of quadratic functions which have the graphs opening upwards. Oh my god, I do want to try it again. Come on, let's work. Work for me. Okay, guess it's broken. I'll go back to Vietnam and buy. Okay. We have another one. The set S such that, with it being a quadratic function such that A, B, and C are both elements of the real numbers, but A is going to be a positive number. Let's define the addition of functions by the usual rule, so for example, that happens, and define the scalar multiplication by the usual rule, so that for example, that happens. Well, the first thing I can see is that if we I'm sure we'd have like closure under addition because positive is going to keep it in positive, and then these associative laws are probably chill, and If we put 0, 0, oh, okay, 0, 0, 0 cannot be satisfied, right? So 1 and 2 works. 3 works. 4 doesn't work because, okay, so 1, 2, 3 works. 4 doesn't, because a is larger than 0, not a is larger equals 0. So 0, 0, 0, or 0 x squared plus 0 x plus 0 cannot exist. Right? Cannot exist. Done. What's something that we could spot? We can spot existence of a negative, like something that tries to cancel it. Well, no, because a can't. I mean, 5 doesn't, because a is always larger than 0, so there is no negative for a. Closure under multiplication by a scalar, definitely not, because just a negative scalar will basically fuck it up, because a scalar that's larger than 0 will force a to be larger than 0, to be smaller than 0. 7 doesn't, or 7, probably not. Okay, so only 1, 2, and 3, to be honest. Or does vector distributive law work? This one works. 8 works. 8 works, because 1 times, ax squared plus 1 times bx plus 1 times c still holds for a is larger than 0. Okay, so 1, 2, 3, 8. I think that's it. 1, 2, 3. Closure under multiplication, probably not. Associative, could we flip it around? -1. No, anything that like defines it. What if 7 works? Closure under addition works. Associative law of addition works. Ooh. Does closure and addition work? No. No, it doesn't work. Probably not. Because we gotta keep it as a quadratic. So, yeah. So we can't have linear, not linear, nor constant. So that tightens up things a little bit. Okay. Maybe that's it. let's read this to ChatGPT. Let me think. My guess is closure under addition doesn't work, specifically because this is a set of quadratic functions, right? So if I had like x squared plus x plus 1, and I had 2x squared minus x minus 1, I'd have a polynomial. I'd have a polynomial degree 2, but it's not quadratic, right? I'm assuming that the quadratic means that, like, fuck. Never mind. Okay, never mind. Wrong. Because a is always larger than 0, x squared works, 2x squared works, 3x squared plus 2x works, 5x squared plus 2 works, right? Because it's just like 5x squared plus 2. Yeah, it's still a quadratic. That's my fault. That's 1. So closure addition still works. Right, so closure addition works. Associative law looks like it works. Commutative law of addition works. Okay, so 1, 2, 3 does work. The existence of a 0 that for all f in f of this is the 0 this is the 0 quadratic, so it doesn't. Okay, 4 doesn't work, but 5, there does exist a negative, but the 0 vectors wouldn't be in S. So I'm assuming 5 still works. 6 doesn't work. I think that's it. Fuck, man. Lambda S is going to be within S. I can see that being wrong because if you just have a negative number, that changes things. Associative law that maybe that associative law of multiplication would work just because I just pull it out and multiply by f. The question I specifically have is, well, firstly, closure under addition works because as long as the a is larger than 0, which it always will be for it to be in set S, addition of two positive numbers would always ensure that the coefficient of a is always larger than 0, and it would always be, in the simplest form, a quadratic any way or another. The associative law of addition would we would probably get the associative law of addition for free, because you could just like add in different order, and it would just be normal addition. Commutative law also as well we get for free. Existence of 0 doesn't work, because a cannot be 0, it must be larger than 0, so we can rule that out. Existence of a negative works. The only question I have is, yes, there is an... Okay, the existence of negative... No, doesn't. It doesn't exist. There doesn't exist. H can't exist. There is none. So 5 definitely doesn't work. Closure under multiplication definitely doesn't work, because a is larger than 0. If we have a negative scalar, that changes our a coefficient to a negative, which is not going to be an s. Associative law of multiplication, we probably get we probably don't get as well, so we don't get 7. Is it just 1, 2, 3? I mean, 7, 8, 9, do we get for free as well? Seven, 8, 9, 10. So even though scalar closure fails, mu times f still works. So like I could still pull the mu out and the lambda out, and I could still say, hey, it's lambda times mu times f is still the same as lambda mu times f. Okay, and then the 8 still works. Okay. Okay, so doesn't. One times f is still f. So 7, 9, 10. Algebraically, because the axiom doesn't care that it is in S, just that it's algebraically correct. Okay. Seven, nine, 10. 7, 8. Yeah, 7, 8. Okay. We prove that v plus v is equal to v for every vector v in a vector space v using the property let's think. Axiom number 8. Scalar multiplication identity. Then the property scalar multiplication vector distributive law could help us write like that. And by definition, since 1 plus 1 is 2, we get that v plus v is 2v as required. That's it. Oh, fuck. Is it scalar distributive law? Okay. So I'll just write the proof out. Vector v plus vector v is equal. Prove a vector v plus a vector v is equal to 2 times vector v in vector space v. Okay, then v plus vector v plus vector is equal to 1 times vector v plus 1 times vector v, and this is axiom 8. And then 1 plus v 1v plus 1v is equal to 1 plus 1 times v by axiom 9. Scalar distributive. Then 2v. So v plus v 2 times v. Good boy. Leonardo Pisa. Q. Like something plus something before, or like two things before it becomes the next thing. Like 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and 3 plus 5 is 8. 3 plus 3 is 6, 3 plus 6 is 9, 6 plus 9 is 15, 9 plus 15 is 24. So that works. Like closure under addition will have any sequence still add to the next one, right? So consider a set F contains a set of elements A1, A2, A3, such that an plus 2 is equal to an plus 1 plus an. Okay. 1. Okay. It looks like a lot of things are satisfied. Plus 2 plus 2 plus 4 plus 6 plus 10 plus 16 plus 26 is equal to 3 plus 6 plus 9, 15, is it 15? 24, right, so closure under addition works. 2 is the associative law works. 3 is the commutative law works, right? Because if we swap these elements around, still good. 4, the existence of a 0. Well, is there a 0 plus 0 is equal to 0 plus 0? So 0, 0, 0 for as many for AI large and equal to 1. Yeah, works. 5, the existence of a negative. If you add two negatives, you actually get something smaller. Let's say I had 1, 2. Sorry, I could not have minus 1 plus minus 1. That'd be equal to 0. And then minus 1 plus 0 is equal to 1. Right? And then 1 plus 0 is equal to 1. And 1 plus 1 is equal to 2. So it'd always be a cumulative, and then 5 doesn't. Because addition can't make it smaller. Like the order is only ascending. Right? That's my guess. Could we do like minus 100? No, let's do like minus 1, minus 2 if we add them together. Right. Could we do like minus 2, minus 1? Like, is there a negative something when you add to it? It's equal to 0. Minus 2 minus 1. If we add them together, we get 1, right? We add those together, we get 0. We get 1. We get 1. We get 2. We get the same thing again. Minus, no, it will always 10. It will always 10 to Fibonacci. So you can't really reverse it. Like if I minus this whole 0, 1 set, I could, like, there doesn't exist like a negative 1 and negative 2 and negative 3. Like this is not a part of f, because minus 1 plus minus 2 is equals to uh, 1, right? And that's not equal to the next element, which is 3. 6. Scalar multiplicative identity. It looks like it works. It probably doesn't work for negatives, right? Minus 3, minus 3, minus 3. When you add minus 3 plus minus 3, it's equal to 0, not minus 6, right? So it doesn't. Right, minus 3 times 1, 1, 2 is equal to minus 3, minus 3, minus 6, minus 9. But that is not in f, because minus 3 plus minus 3 is equal to 0 and not equal to minus 6. 7. Scalar multiplicative. So I'm assuming if it's both that and it satisfies that, it probably works. Yeah, since, I mean, algebraically, like lambda times lambda mu in q lambda like 2 over 3 times 4 over 3 is equal to like 8 over 3 is still in q, and it doesn't matter the order really if you just multiply it by the Fibonacci sequence. The scaling works. 8 scalar multiplicative identity works. 9 looks like it would work. Okay, let's try it actually. Like 2 plus 1 times a vector A, which is defined by 1, 2, 3, 5, 8. Let's do like minus 1 equals 2 times 1, 2, 3, 5, 8 minus 1 times 1, 2, 3, 5, 8, which is equal to like 1, 2, 3, 5, 8. So that works. And 10 looks like it works. So only 5 and 6 doesn't work. So open set 1, 2, 3, 4, 7, 8, 9, 10. Really? Scalar A's got Q. 2 over 3. 2 over 3. Sorry. 1 over 3 plus 1 over 3. 1 over 3. 2 over 3. 3 over 3. 5 over 3. 8 over 3. And it works. I don't like this. It's actually really like you don't know what you did, or you don't know like why it's like partially correct. Closure and addition has to be correct. The associative law looks like you could just add them in any order, it'd probably work. Commutative law definitely works. Existence of a zero, yeah, right? So if like 1, 1, 2 plus 0, 0, 0, we still get 1, 1, 2, which is still going to be an F. Existence of a negative, and it would be a zero vector, which probably doesn't make sense at all because yeah. Closure into multiplication by a scalar definitely doesn't work. Associative law, two times one, 2 over 1, yeah, that works. 7 works. 8 works. It might be something wrong with 9 and 10. I actually don't see anything wrong with it. I do want to see what happens. Join us on Rubric. What does sanctioned in? What do we get? $10. 30% weekly membership. 2 weeks, 1 year of discounted day passes. $6.
If you want to make some new friends, chuck a cheeky flex, hit some PBs or test your limits. Or just have a great time. Barbell Club.
Sorry, my bad. I want to get this done and over with. Jeez, you scared me. Hi.